Yeah. Fine. So the angle alpha basically decides the optical configuration, where in inline holography the angle alpha between object beam and reference beam is 0, whereas in the case of uh, it should be non-zero. Okay, so angle alpha between object and reference beam is non-zero, which essentially leads to carrier fringes that will be generated in the CCD plane. So uh, essentially in the CCD, if I only look at the CCD plane, when the plane wave is illuminated at an angle with respect to the optical axis, so this is the reference wave, direction of propagation of reference wave. So due to this, so if you look at this plane, the CCD plane, the reference wave is reaching at an angle. So what happens is that due to this angle, each point, each pixel on the CCD will experience a different phase due to the angular illumination. In the case of on axis or in line holography, since this plane is illuminated by a plane wave traveling perpendicular or in the direction of the optical axis, each pixel on the CCD will have the same phase as the phase of the plane wave, right? But due to the angular illumination, the phase experienced by each pixel is different. And how is the phase changing? The phase is changing linearly. That's why you see that the phase expression associated with the reference beam is a linear term, right? And it has associated frequency that is nothing but the slope of the wavefront, uh, which is given by fx and fy. The advantage of this configuration is that the three components, that is the DC component, virtual image and real image, they are specially separated and one can visualize them. Otherwise, all of these three quantities generally overlap each other in space. So I will briefly show you the MATLAB demo which we saw previously uh, to so this is the MATLAB demo here. In fact, I have not shown the complete image. So let me show you the complete image. So this is a complete image where you can see that this is a DC part, this is a virtual image, this is a real image, and you can see the object is getting focused at a particular distance, and after that it becomes blur again, right? So by we have analyzed mathematically also that when you substitute this expression of reference into this, when ZR is equal to Z0 or minus Z0, the quadratic term associated with this x square, xh square plus yh square uh, uh, is eliminated from this expression, and that is the distance where you see the object to be in focus. Otherwise, now if I zoom in this part, you can clearly see that it is blurred, right? It is not sharp. So the reason is that at that location, the plane where the reconstruction is performed, that is ZR, is not equal to Z0. So when ZR is not equal to Z0, this term xh square plus yh square divided by ZR remains, and that basically is a blurring operator associated with the quadratic phase term. So that is, I think we have analyzed it, if you remember. Yes. So here we have seen ZR equal to Z0 and ZR equal to minus Z0 will lead to either virtual image or real image in focus. So that is done. Now we have yet to discuss the lensless Fourier transform holography, where instead of plane wave, your CCD is illuminated with spherical wave. Okay, not plane wave but spherical wave. Now remember, the illumination is again at certain angle. Okay, so it has the reference in this case, as you can see here clearly, not only has the term associated with fx into xu, but the quadratic term associated with xu, that is xu square and yu square. So this is the expression of reference beam, this one, right? Because now we are using not plane wave but spherical wave, which is given by this. Although this is, remember, this is an approximation. Here also we are considering the paraxial approximation, where the spherical wave is reduced to quadratic expression, right? Considering ZU and XH, sorry, XH and XU being very small compared to ZU. Under that assumption, we get this quadratic approximation. I hope you remember that expression we derived. Now, if you substitute this reference wave in the general formulation of hologram, where was it? Yeah, here. In this expression, if you substitute it in this expression, the simulated reference wave, this for spherical reference wave in the case of lensless Fourier transform holography. So how does the setup looks like for lensless Fourier holography? Here, as you can see, the object is placed at a distance z0 from the object, but reference wave is not a plane wave, but it is a spherical wave which is derived from the point source, right? So we know that a point source generates spherical wave, right? So this one. So it will generate spherical wave. And remember, each point on the object is also generating a spherical wave, right? So as you can see here, in this, here, two waves which are spherical in nature are overlapping and forming an interference pattern on the CCD, right? Now, if you substitute the simulated reference wave in this expression and expand it, then again here you will have three terms, one with DC, one with the virtual image, one with the real image, right? Now, again, if you look at the expression here, the quadratic term will get removed. ZR will get removed when you put it equal to Z0. Okay, so in this case, as you can see, ZR, the this is a condition. So let me write. Effect of quadratic term, quadratic, I will write quadratic phase term, because you see here this expression xh square plus y square divided by z0 is appearing in the phase term, right? E raised to I pi by lambda into this. So quadratic phase term xh square plus y square divided by zr. So when you satisfy this condition, then the advantage is that in the both the expressions of the um, virtual image and real image, the quadratic term gets removed. Okay, when you satisfy this condition. Now in that case, you see what is the reconstruction? Reconstruction boils down to nothing but simple Fourier transform of the hologram. So if you record the hologram in this setup like this, where what is the difference? The spherical wave is used as a reference wave as opposed to the common way of using plane wave as a reference. And the other condition is the reference, so the source is kept exactly in the same plane as the object, right? So ZU is equal to Z0 in this case, right? In this case, ZU is equal to Z0. So what is the reconstruction distance? Can someone tell? When ZU is equal to Z0, when you put it in this expression, what is ZR?
So Z0 by 2.
Sorry? Sorry?
So Z0 by 2.
Z0 by 2. Are you sure? You see,
So 0.
1 upon ZR is equal to 1 upon Z0 minus 1 upon Z0. What is ZR?
Okay, sir. 0.
Huh? 0?
So infinity.
Infinity, no? Infinity, right? Because this term is 0, no?
Yes, sir. Infinity.
So ZR is
Yes, sir,
infinity.
infinity.
So effectively, this term gets nullified when you substitute ZR equal to infinity, and in that case, your reconstruction, if you simplify this further, will become simply a Fourier transformation of the hologram. So previously, what did we do in the reconstruction in the case of inline holography, or if you look at the Fresnel transform, how do we calculate? You multiply H with R and compute the uh, the uh, product of this term with the product of H into R, and then calculate the Fourier transform, right? So there is a multiplication involved with H and R and this term, and then you take the Fourier transform of this. On the other hand, in the case of convolution approach, you take the Fourier transform of this product H into R and the Fourier transform G, which is the basis Fresnel basis function, and then you calculate the inverse Fourier transform of that, right? This is what we did. But in the case of Fourier holography, the advantage is that you actually simplify the calculation by arranging this setup in a particular manner such that reference point source is kept in the same plane as that of the object. So ZU is equal to ZR, and in that case, sorry, ZU equal to Z0. In that case, ZR reconstruction distance becomes infinity, and when you substitute that value in the expression of the intensity, then we realize that the reconstructed image, or reconstructed, rather not image, but the reconstructed optical field, which is a complex field, can be derived by simply calculating the Fourier transform. You don't need to do any other operation. No multiplication with R is required. Okay. So with this, both the reference virtual and real image will be at focus. So let me show you that part. I think that we did not look at the mathematics behind that in the previous class. So yes, you can see here both virtual and reference. So this is real image. So it is at focus. Even this is at focus. In the other case, we saw that this was blurred, isn't it? Right? Only one image was at focus. So this is the advantage with lensless Fourier transform holography. Advantage is not having both the images at focus, but the advantage is lesser computation cost. Now, one can even have the numerical reconstruction with adjustable magnification. Right? So in this case, in the case of inline holography, the magnification is unity, means whatever is the size of the hologram is the size of the object in the case of inline holography. On the in fact, not in inline, but in the case of convolution based approach, the reconstruction is such that, let me write it here. Is it written somewhere here? No. So in this, the resolution of the reconstructed image is equal to the pixel pitch. Okay, so whatever is the size of the CCD will be the size of the field which is being reconstructed, and the pixel size is equal to the reconstructed image size. That's why delta xi is equal to delta xh. On the other hand, in the case of Fresnel, we saw that delta xi is not equal to delta xh. In fact, it is lambda zr by n into delta xh. This is what we derived, right? So in this case, the reconstructed image resolution depends on lambda, depends on the reconstruction distance, and as you can see that as you go far away from the object, or the if the reconstruction distance is large, then the reconstructed image resolution is reduced, means delta x is increasing, right? So the resolution is decreasing. So, and it also depends on the spatial extent of the CCD. Why spatial extent? Because n into delta xh is the physical size of the CCD along x, and m into delta yj is the physical size of the CCD along y axis. Right? So it depends on all these parameters. On the other hand, in convolution, it is equal. So in the case of numerical extension with adjustable magnification, one can actually change the size or perform the user dependent magnification. And how this magnification is defined? It is defined as delta xi divided by delta xh. Now in the case of convolution approach, this magnification factor gamma is equal to 1, whereas if you look at the expression for delta xi in the case of Fresnel transform, gamma is how much? Delta xi is equal to lambda zr divided by n delta xh divided by delta xh. So it becomes delta xh square, right? So this is the basic magnification associated with Fresnel transform. Okay. Now there is a mathematical manipulation which is being done in the expression of Fresnel transform, which is known as Fresnel-Bluestein transform, which allows you to use a parameter gamma such that the user can set the required magnification depending on the requirement. This is the expression for the discrete. This is a discrete version of Fresnel transform, right? If you remember, this is a discrete version of Fresnel transform. Now, what is being done here is that the if you look at the previous expression or Fresnel, so you see this is the discrete transform. There is a term before the integration. So if you look at this one, yes, you see this term, we generally neglect this term because it is independent of the object. But if you utilize that term and manipulate it in such a manner that this delta xh square term is actually obtained by the, so I think it is better if I go back here. So you see, we had used this expression and we expanded it like xh square plus 2xh xi plus xi square, and the term associated with xi square was taken out of the integration, right, in the case of Fresnel transform. If you don't do that and if you focus on the discrete implementation of this integral, this is what is done in the case of Fresnel-Bluestein, and just keep this term together, then you define gamma because we have defined the magnification delta xi by delta xh. So this term is delta xh minus delta xi. So if you take out the delta xh common, then you can see that there is a term called 1 minus delta xi divided by delta xh, which is nothing but 1 minus gamma. And there is a term associated with only gamma here because delta xh into delta xi is equal to gamma square. No, there is something wrong here. Yes, delta XH square is being replaced with where is that term one? I will write that expression better. I think the same expression I will write, then it will be clear. You see the same expression here, just that it is implemented in a discrete format. Discrete format of Fresnel is not written. No, it is not written. Fine. So this is the same thing, just that this is implemented in a discrete format, and we have taken this term inside the summation again in this case. Okay, now when we define gamma as delta xi by delta xh, then this is delta xh square. So you can see this is delta xh square into gamma. Delta xh square into 1 minus gamma, and there is one more term. Why this is delta xi into delta xh? It will be gamma delta xh square. Yes, gamma delta xh square. Fine. Right. So there are two terms, one with 1 minus gamma, one with 1 gamma. And what essentially what you get is that in the case of adjustable magnification, the reconstruction is involved with two products, one with this and one with this. So if you consider this normal Fresnel transform reconstruction, it involves the product of h with r into this quadratic term, right? And then we take the Fourier transform of that. On the other hand, in the case of adjustable magnification, there is a product of h into r with a quadratic term, which involves a magnification factor, and then there is another quadratic term which involves a magnification factor gamma. Here it is 1 minus gamma, here it is gamma, right? And you then take the product of these two and take the Fourier inverse of that, and that is how you compute the adjustable magnification. Now, if you substitute gamma equal to 1 in this, okay, then you will get a particular expression associated with unity magnification, which is in the case of inline holography, right? But if you substitute gamma equal to this lambda zr by n into delta x square into this, then you will see that it is nothing but the expression associated with off-axis holography with implemented with Fresnel transform. Okay, so I will show you some demo regarding the adjustable magnification with Fresnel-Bluestein transform. Now, here what I've done is that if you remember, I told you that our gamma associated with Fresnel transform is lambda zr divided by n into delta x square. So this is how I have defined it as gamma 0. Lambda zr here is d. So n into delta x square, whatever it is the same delta x and delta y. So n into delta x square, and this is the denominator, and in the numerator is lambda zr. So this is my gamma 0, means the magnification associated with Fresnel transform. Now, if I scale it according to that, so let's say if I keep the same, so I'm basically with keeping gamma equal to gamma 0, I'm actually reconstructing the hologram with Fresnel transform, not Fresnel-Bluestein. Okay, so this is having the magnification of lambda zeta divided by n into delta x square. Now, if I want to scale it, let's say, now I will scale it with gamma 0 divided by 1.5. Now the effect is such that you see that the spatial extent of the object has increased, right? As if I have zoomed in into the object, isn't it? So it was of this size previously, as you can see. If I take only this part, if I take only this part, now this part is zoomed in here. Now how this zooming is performed? This zooming is performed numerically, not optically. Okay, of course the image resolution has reduced. The reason being that the delta xi is more, so the fineness of the image is reduced here, of course, but the image size, whatever we are seeing, has increased. On the other hand, if I choose to have the scaling in the opposite way, where gamma is 2 times gamma 0, then you will see that the size will reduce. Here you can see the size is reduced as compared to the normal Fresnel transform. The object is same, nothing will change in the object image. However, you can see the replicas have come because of the repeatability associated with the Fresnel transform. You can see there are multiple copies, but the actual information only is this part, right? But you can see that in the same size of the image, there are 4 copies of the object, 4 copies of the DC part, 4 copies of the virtual image. So effectively the object size has reduced. On the other hand, when I selected it to be gamma 0 divided by 1.5, the image size is such that you can see that portion of the virtual image is overlapping the portion of the real image, defocused real image, is overlapping on the virtual image. That because the size has increased and the CCD image size is not capable of capturing the increased magnification. Okay, right? But you can easily visualize the magnified image here. So this is one. So you can see this is with increased magnification greater than gamma 0. This is less than gamma 0, right? And there is one option. So if I get it to be equal to gamma 0, then there will be with unity magnification. Yes, so this is with magnification equal to gamma 0. So we have 3 options. So I'm just showing this is with gamma equal to gamma 0. This is with gamma equal greater than gamma 0. Okay, and this is with gamma less than gamma 0. And how is gamma 0 defined? So I will write it here so that it is better for your reference. So gamma 0 is lambda zeta divided by n into delta x square. Okay, fine. Now how can one suppress the DC term in the, because you can easily see that in the reconstructed image, this is basically clouding the intensity of this reference is basically clouding the image, right? This is so bright that it becomes difficult to visualize. So if you look at it from the on the logarithmic scale, but still it is not that clear even if you look at it at the logarithmic scale. So if you can remove the effect of this thing, then it can probably give a better result. In fact, here I have already done that, but if I remove the DC part by subtracting the mean of the hologram from the hologram, okay, so I'm subtracting the mean. Why? Because we know that the DC part is associated with 0 frequency. So when I subtract the mean, what I'm actually doing is I'm subtracting the low frequency component from the image. So you can see that this has reduced to a certain extent, isn't it? And this looks brighter in comparison to the surrounding pixels, right? So this is what is known as suppression of the DC term, and it has reduced to a certain extent. Let us now look at how it looks. So this is not a good option to take the log part of this. So this is a better image, right? There are other methods based on the logarithm, taking the logarithm of the hologram and all, but it is not essential for our discussion. Just remember that the simplest option is that you take the hologram, subtract the mean of the hologram. Remember, hologram is nothing but an intensity pattern. So you are basically calculating the mean intensity of the image. Subtracting it will effectively remove the contribution of the DC term. Because why we need to remove DC term? Because it is not carrying any information on the object, right? So it is an unessential term in that. Now we'll discuss about something about digital holographic interferometry. Now I will discuss it from the application perspective, so that you will appreciate the advantage of this technique. Now, if you remember our discussion on the different interferometric setups which we discussed, especially speckle interferometry, where we used it for deformation measurement, right? So we considered that, let's say there is an object, we illuminate with light, and we recorded the interference pattern and all. Fine. Now, when the object undergoes any change, physical change, let's say there is such a small deformation. Now this deformation is in micron level, then there will be a change in the phase of the light which is being scattered, and that is a principle which we had used, isn't it, to obtain the deformation at the micron level. The similar principle is used with digital holography. However, in this case, the thing is that what you need to do is you record the hologram of the object before deformation, and you record the hologram of the object after deformation. Okay. Now, what has actually changed in both the thing is the surface has undergone the change due to deformation. Now that change basically gets reflected into the phase of the light which is being scattered. Now the holography, as we know, just saw, that allows you to reconstruct the optical wave field scattered by the object in the object plane, and the object plane is x0 y0. So what you do is, once you record the hologram before deformation, you reconstruct the hologram and obtain the optical wave field. So this is optical wave field. Remember, it is complex in nature. You can see this optical wave field before deformation. Okay, and this is the optical wave field after deformation. Now, how do you obtain this optical wave field? By reconstructing the hologram using the methods which we just discussed: Fresnel transform, convolution, whatever it is, whatever you use, doesn't matter. Now, what actually happens is that along with phase, there is a change in amplitude also, but we assume that it is not carrying the information on the deformation. The deformation information is encoded in the change in phase. So the phase reflect scattered by the object. Remember, this is a random phase. Okay, please remember, this is a random phase. So this is random. And this is also random, but the change is deterministic. Okay, now you have two complex signals, AB into e raised to j5. So I will write AB e raised to j5 into AA e raised to j5 plus delta phi. Right now, when you take the complex conjugate multiplication, then these become minus. So this term phi gets cancelled, that random term, and the phase is only associated with the deterministic component, right? And then you have to take angle or angle of gamma x0 y0 will give you delta phi in wrapped form. Now you see that the advantage with digital holographic interferometry is that you don't need any phase shifting in this to obtain phase. Why? Because you have not obtained the data in terms of intensity, such as a plus b cos phi. You have directly obtained it in terms of e raised to j phi, right? So since you have already obtained it, there is no need of phase shifting. in the case of digital holography. So one can utilize this. So only 2 holograms are required before deformation and after deformation. So I will show you a demo for this. You see, let me also show you the you see, this is a reconstructed image. Basically, this is an image of an aluminum plate, okay, which was illuminated with a laser source, and it was recorded with off-axis setup. The aluminum plate is a circular disc of aluminum, and if the cursor is visible, then you see the point where I'm locating approximately is the point where the deformation was applied. There was a needle at the center. The deformation was applied by pushing the needle, and the aluminum plate undergoes a deformation in the out of plane setup. So the setup is like this, exactly similar to your ESPI setup. So the setup for deformation measurement in this case, in the deformation measurement was like this. I'll just show. There was an aluminum plate here, was illuminated with a laser light source. There was a camera and a reference beam. So this is R, and I will use a different color. So this is the light coming from the object. So this is O. Okay, and the CCD is CCD recorded the hologram. Okay, so remember, reference is coming at an angle. So this is a off-axis setup. Okay, and the aluminum plate was a circular plate, and at the center the deformation was applied. Okay, so let me see if I have the photograph of that or not. Such a photograph was there, I saved it. You see, like this. See, the object was like this. This is aluminum plate, you see, and there was a micrometric screw provided. When you rotate it, it basically deforms. You can see that there is a aluminum, and the center you applied the deformation. Okay, and this plate was illuminated with laser and laser light. And when I recorded the hologram and reconstructed, this is the object image. Of course, it is illuminated uniformly. You get a nice image, and remember, this is the amplitude image. And when I take the phase, you see in this region the phase is random. Everywhere phase is random, but in the object region also the phase is random. So now I will show you that when you subtract these two phases, subtract the two phases in this region, object region, the phases obtained before deformation and after deformation, this is what you get. Okay, so what is this? This is nothing but delta phi. Okay, this is nothing but what you are seeing here is delta phi, and it is corrupted with speckle noise. You can clearly see. You can see that it is not clean. It is corrected with speckle noise. The reason is that after deformation, we have assumed that phi, the random phi, is same in both cases, but it is not the case. After deformation, even the random phase also undergoes a change, and that is appearing in the form of speckle. But still, one can clearly visualize that there are contours which are indicating the object which has undergone the deformation. And if you unwrap this, you unwrapping algorithm, and you can see that how the plate has undergone the deformation. Okay, and if you calibrate it in terms of microns, then you will be able to measure the deformation on this plate at each point. And it is very much useful from structural mechanics point of view for non-destructive testing of object. I have already shown you the applications of stereography ESPI in different domains such as aerospace, aviation and all. Okay, so this is a basic principle, and one can utilize the holographic principle also, which is termed as digital holographic interferometry. So briefly, you record the hologram of the object before deformation and after deformation. Subtract the phases, you will get a nice phase map as shown here. Okay, and all this experiment was done by us only. So it is with this phase difference. So you can even visualize that how the plate must have undergone the deformation, that at the center the deformation is highest, right? And at the boundary, because it is fixed, as you can see here, it is fixed, so the deformation will be 0 at the boundary. Okay, fine. Now other application of DHI, digital holographic interferometry, is for refractive index or temperature measurement. Okay, now in the same setup, I used the same setup. That aluminum plate was there, same aluminum plate, no difference, same aluminum plate was there. Now here, instead of applying the deformation to the aluminum plate, what I did was that, remember, the phase change can occur anywhere in the path of the light. Now the moment the light is hitting the surface of the object and it is reaching to the CCD, if there is any variation, in the medium in which the light is traveling, which in this case is air. So if the air refractive index varies, then there will be change in phase. Okay, so in the case of deformation measurement, we assumed that it is not changing, right? So to purposefully change the refractive index, what I did is that I kept a candle in between. So if I draw it here at other angle, so let's say this is my aluminum plate and this is a CCD. The light was illuminating and the object wave was generated and reaching the CCD. The reference was coming at an angle. Okay, so this is R, this is my O, right? So I recorded the hologram with aluminium. So what I did is I kept one candle here. I kept one candle in this, at this position. I did not lit the candle at this moment. Okay. Now I recorded the hologram, and the next hologram was recorded when I lit the candle. So the flame was there in the path of light which was coming from the aluminum plate to the CCD. Okay. So with this, what we did is that we actually have changed the refractive index of the medium in which the light is traveling. I mean, why refractive index will change? Because of the temperature change introduced by the flame. Now, in both cases, because the refractive index has changed, the phase has changed, so that delta phi in this case will not be due to deformation, but due to the refractive index change. Right? Now, this delta phi is basically nothing but can be calculated as 2 pi by lambda integration 0 to L. So what is L? The path from object, this aluminum plate to light to the CCD. So along this path, if I integrate the variation in refractive index, okay, delta n is a variation in refractive index. So if there is nothing in between, then this quantity is constant. I can take it out. Delta n is constant, but delta n in this case is function of z. and it will be also function of x and y. Okay, so if this is the case, then one can encode the variation in refractive index information in the phase of in the in the form of delta phi and utilize it for measurement of refractive index. And we know that the refractive index has changed due to temperature, so one can even measure the temperature, and it has been used. So there are studies which has been proposed to measure the flame temperature using DHA, and the same principle was used. So I will simply show a demo here where a small experiment was done. So you can see that this is the phase before aluminum plate was lit. Sorry, the candle was lit, and this is the thing when the candle was lit. So I will also show you the. Yes, you can see here. This is the candle which was kept in between, and it was not lit before, and this is the image before lighting the candle, and this is the image after lighting the candle. Now if you look at the amplitude image, okay, so let me keep it up side by side. You see, if I have these two images together, you see there is no change as such, right, which is visible in the amplitude image, right? Why? Because the refractive index variation will bring the change in phase. And how does that phase change looks like? This, but it is random, right? We can't see, but the change is not random. So when I subtract these two, we obtain this. So it clearly can see that this is the candle. You see, this is the region which is of the candle, and the surrounding region. So you see that the circular region is of the aluminum plate, right? Because I had kept the candle in between, the change in the refractive index brings a change in phase, which is clearly following the pattern of the flame, right? So one can even do the unwrapping of this. Have I done? I think I have not done the unwrapping. Let me try doing it now. So you see here, now you have a nice profile of refractive index variation. So in fact, you can even calibrate it to measure the temperature, right? Of course, the center part has high temperature, you can assume like that. So, and surrounding how it is changing. It was a very crude experiment, but still you can see that you get a nice pattern of changing the refractive index of air due to flame temperature. Okay, fine. One can even utilize the digital holographic interferometry for the purpose of vibration measurement. Okay, there is a slight mathematics involved in this, because in the case of vibration measurement, what you actually do is that, remember I told you that a CCD or CMOS camera have a particular exposure time, right? So when you are exposing the light coming from the object and reference to the CCD, it is basically accumulating it over time. The exposure time might be in milliseconds, sometimes in microseconds, sometimes in seconds also, okay, depending on the light condition. Now, for the purpose of vibration measurement, what you do is that if the object, let's say in the place of aluminum, if I put a vibrating object, it is vibrating at a particular frequency. So if the rate of vibration is much high compared to or it's a period of vibration is much small compared to the exposure time, then what CCD is going to record is the effect of multiple vibrations or multiple, what you can say, waves generated by the vibrations. The accumulated effect of that will be captured by the CCD. Okay, and that hologram is actually the, you can say, I will write it down in a simple form. So whether I put it or not, no, let me write it down for you. So I will not go into the more details of the mathematics of it, but to just appreciate what is done. So the intensity or the hologram h xh yh, what you record is the integral of the intensity, that is r xhyh plus o xhyh. Oh, sorry, dt. What is capital T? Capital T is the exposure time of the camera. Okay, this is exposure time of camera. So this is the instantaneous intensity. Okay, and we are integrating it. And why we have taken this? Because in the place of O, basically your O itself is the integration over time. Okay, so OXH YH has another variable called T because it is varying with T. Okay, so when you substitute the expression for O, or in fact when you calculate the four, that remember in this term there are four terms, R star plus O star plus R O star plus R star O. So if you focus on this term, okay, in this and take the integration, then the hologram will be generated corresponding to the vibrating pattern of the object, and it basically generates the basal fringes. So that there I'm not going for the details of that. So you basically get fringe pattern which are basal fringes. They are called as basal fringes. So I will just show you how they look like. So what I did is I had used a simple what was that, this loudspeaker from a radio. Okay, so the loudspeaker from a radio was used, and I drove it at different frequencies using a function generator. So let us start with, so I don't know how much was the 125 millisecond was, I think, was the exposure time. I don't remember now, but you see that this is the pattern you get. Basically, this is a circular loudspeaker, you can see, and you can easily see that there are fringes which are generated. Right, there is a nice pattern. Now, if you look at this pattern, and if I change the frequency to 8 kilohertz, so it was 7.5 here. I changed it to 8 kilohertz. Then it looked like this. You see, it had changed, isn't it? It had changed. Now, if I make it to 8.5, it will be different. It is clearly visible, right? It is different, and I took it for 9 and 9.5 as well. So for 9, you have a nice pattern. You see, this number of the fringe lobes, you can say, are different for different frequencies. Now, if you do the same thing with a load on the loudspeaker, so what I did was I actually used a small object and I pasted it or stuck it on the surface of the of the speaker, you see, if it is visible to you, I don't know, but there is a shiny part on this here, the cursor I'm showing. So this was at 9 kilohertz. Okay, so at 9 kilohertz, without the load or the object which I kept, the fringes look like this, right? But with the object on the surface, you can see that due to the presence of this object, the effective mass of the surface has changed, right? So the vibration pattern has also changed. So this technique is basically used to identify if there are defects on the surface, if there is any crack. So if there is any crack, then that variation immediately appears in the variation in the speckle, in the fringes, vibration fringes, as you can see. So these are the different applications of digital holography interferometry. So so with this I will stop, but I would wanted to discuss other part also. Maybe I will cover it in the next class. Applications we'll discuss in the next class. Thank you.